Here's a problem here which might look deceptively simpler than the other ones that we've worked in this video series here that involves three masses, M1 and 2, M3. M1 and M2 are connected by a rope, M2 and M3 are connected by a rope, and the whole system is being pulled by some force F, maybe some kid's pulling it, and this force is only attached to M3, but the kid is, for whatever reason, pulling like this little train of toys to the right like that. So the question would be, if this was a T1 in this rope right here, say there's a T1 that existed down here, what is T1? If this is a T2 down here, what is T2? So as the kid or the child or whatever the force acts on the system, how are those tensions related? And the other thing I might ask is, what would the acceleration of the whole system be? So very similar type questions that we've seen before in these types of problems, but now it's just sort of a group of three blocks on a line like that. So what we'll do is we'll just proceed again with our normal plan here, is that we have Newton's laws available to us, ready to go at any time. We're going to identify the forces, we're going to put a sign convention in there, then we're just going to go ahead and fill in equations 1 and 2 and see what we get. So the first thing we'll do is just go ahead and identify those forces. So it looks like M3 has this force acting on it. And here's a rope in here, and tensions always pull away from the points of contact, and we've decided this called this T2. So there'll be a T2 in there. And it also has its weight on it, M3G. And there'll also be a normal force on here. We'll call it N3 because it's the normal force on mass 3, also to denote that it's going to be different than the normal force on the other masses. M2 will also have a tension pulling on it in the opposite direction like that. There'll be a T2 that way. And M2 is going to sort of point down like that. There's its weight. And the normal force is going to point up. We'll call it N2, something like that. So there's going to be a normal force straight up like that. We'll proceed on with M2 over here just to finish up. If we're saying this is T1 in this rope over here, there will definitely be a tension pulling away on M1 like that, a T1, something like that. Tensions always pull away from the points of contact, whether you're sort of ready to grapple with them or not. This is the only way this rope can possibly interact with these masses, that is by pulling away from them. M1 here is going to be downwards like this with an M1G, and it's also going to have an upwards normal force, N1, something like that. And because we declared a T1 in this rope here, the T1 is going to be pulling away, something like that. So that's sort of the entire force picture. That completes step 3 here, which is identify all the forces on it. Now this problem would be incredibly difficult if you now didn't sort of train your mind to focus on these things one object at a time. So what I'm going to do is I'm just going to draw a big circle here around this mass and say I'm now going to use Newton's law. I'm going to fill in these two equations here for just that mass within that bubble there. But before I do that, I guess I should put the signs in the whole system here. We'll call it down negative across the board for all of these things. That way up is going to be positive, up is going to be positive. I think we're used to that. And we'll call, in all the cases here, we'll call right positive and left negative. So this force is going to be positive. This tension is going to be, it's going to get small in here, but this tension is going to be negative right here. That means this tension here is going to be positive. That means this tension is going to be negative. That one's going to be positive right there. So that's where the signs fall out. I couldn't get them next to the letters, but we'll be careful to get it right now when we fill in Newton's laws. So once again, let's look inside this green circle here and see if we can fill out Newton's laws here for M1. And what we'll get, I guess the most interesting is probably the x this way here. So the x acceleration on M1 here looks like it's just going to be T1 divided by M1. I don't see any other x forces. That's all I'm going to have there. And I can look in the y direction also and get that it's going to be N1 minus M1G divided by M1. Again, I'm skipping a few steps. I'm not explicitly writing out the equations, but all I've done here for AX and AY is filled in these two equations. Given that I've done steps 3 and 4, identify the forces and the signs now, I'm just filling in the sums. I can do the same thing for M2 here. In particular for M2, different again, but if you can get your mind trained on looking inside and only focusing on one object at a time, let's just look right inside this big blue circle here on M2, and what am I going to get? In the x direction here, my AX is going to be minus T1 plus T2. Those are the two tensions that look like they're doing a tug of war on the mass. T2 is pulling that way, T1 is pulling that way. And there we go. You see the direct interaction right there with a sign in there. And if I divide all that by M2, that gives that x acceleration on M2. And in the y direction, I have something similar as in the other mass. I'll get N2 minus M2G divided by M2. That's the y acceleration for that system there. Lastly then, I'll look at M3, which is one that leads the whole system right there. And once again, if I can just train myself to apply Newton's law independently on each object as if the others don't exist, just look inside this last blue bubble right here and see if you can figure out what these forces are going to be. In the x direction here, I'll have a plus F minus a T2, something like that, divided by M3. That's the x acceleration. So there's the force that's causing the whole thing to move. It's being pulled also by a t2 to the left like that, and you divide by m3, and there's that equation for ax. Ay is going to be similar to the others. We have a normal force up, we have a weight down, m3g divided by m3. That sort of completes it for us. So you look at what Newton's law has done for us here. It has sort of allowed us to generate a bunch of equations here. We have two equations generated for m1, one for ax and one for ay. We have another two equations generated here for m2, one for ax, one for ay, and another two equations generated right here for m3. So we have 6 equations we've generated, and those are the ones that describe the motion of the system. Now what we have to do is use a bit of intuition and see what we can pull out of these equations here insofar as maybe solving the problem goes. So what you can realize then is that what we've covered in another video on objects linked by ropes is that their accelerations are the same. So what that means is because m1 is tied to m2, m2 is tied to m3, the acceleration of all those blocks is going to be the same number. So m3, for instance, can't start zooming off to the right with an acceleration of 5 meters per second if m2 and m1 don't also follow with the same acceleration. So what you conclude then is that this ax right here, this ax right here, and this ax right here are all going to be the same thing. So you can equate and plug those things in as all you might need to do. So what I'd recommend, I'm just looking at the algebra here, it can get a little bit messy, I suppose. But what you could probably do then is just do a little bit of rewriting here, in particular the one for m1 there. You can write that as the acceleration is going to be t1 divided by m1. You can certainly write that. For m2, you can rewrite that as minus t1 plus t2 divided by m2. You can certainly write that. And then for the last one down here at m3, you can write form its acceleration will be plus f minus t2 divided by m3. So the reason why I did that is just to emphasize that the acceleration of all these things are the same, so you can dispense with the x notation and say, hey, it's all the same acceleration. Why don't we just use that? So what I'd recommend doing then, a bit of algebra now, which I'll not do in the video because it's too long, I would solve this for t2 and plug in for that t2. I would solve this for t1, pretty easy to do, plug in for that t1. Then what I would do is after you do those plugins, this equation that you plugged everything into is going to be one big equation now, which looks like you can just solve that for a. You'll get a equals something. And that'll be sort of your final answer. That'll be the acceleration of the system. And it will be a function of m1, m2, m3, and there you are. Now, if you want to get those tensions to come out, which is probably the second part of the problem, the next part of the problem is to try to predict, well, what are T1 and T2? I think you probably have all the equations all drawn out and ready to go to do that, just a matter of doing it. Because once you have the accelerations here, which you do, this A is going to come out, you'll get the acceleration right here. You can use that acceleration, say, right up in here. If you know what A is, you can plug this A back into this equation here and solve for T1. That'll give you T1 right off. No problem there. And then once you have T1 and A, you can go back to this equation right here. You can plug T1 in for there, A in for there, and solve for T2. This is where your T2 will come from. So you have your T1 and T2. There's your tensions right there. So once again, recap, fairly long problem, 3 masses like that. But all we did was apply Newton's law, or recognize that they're there and available for us. We identified the forces, we identified the signs, then we just filled in equations 1 and 2. It got a little bit messy, but Newton's law generated 2 equations per block for us. And from that, and a bit of algebra down here at the bottom, and intuition to recognize that all these AXs are the same number because the objects are linked by ropes, lo and behold, we're able to make some accelerations fall out. Now, what I've drawn down here looks like a big mess, and it is. There's a bit of algebra to do in there, but it's nothing you shouldn't be able to handle to get those accelerations and the tensions to fall out. And then just one last thing, what about those other equations that we never said anything about, in particular the ones that involve AY? So what about this equation right here, this equation right here, and this equation right there? Well, they didn't really help us in the problem. They were there and they're correct. They just weren't needed. But what they would eventually tell us, if you were so interested in knowing, is that none of these blocks are ever said to lift off the surface or dig into the surface. M3 stays put, M2 stays put, and M1 stays put. And by staying put, I mean along the y-axis. None of these blocks ever moves along the y-axis. So that means that in this case here, this AY is equal to 0. And this AY here is equal to 0. And this AY here is equal to 0. All those y accelerations are 0 because the blocks never move. And so what that'll end up giving you if you work on it here is that M1 is equal to M1G, N2 is equal to M2G, and M3 is equal to M3G. It just gives you the normal forces to pop out. Could be useful in some potential problem where maybe there's some friction or something like that. Like, for instance, if the path right under this block here had some friction on it, for instance, it was moving, you would need the normal force in order to process the friction. But it doesn't happen in this problem, so these normal forces just sort of go unused. So there you go.